Hi everyone, and welcome back to another video about calculus, and today we're going to talk about something called implicit differentiation. Now, in order to understand why we need implicit differentiation, the first thing we need to do is understand what the word implicit means in a math classroom. So let's revisit something called a conic section. Now, conic sections are things that you get when you take a cone, so picture in your mind a three-dimensional party hat, like the cone-shaped party hats. And if you take that cone and you slice it in different ways. Sometimes we'll slice it parallel to the base, sometimes we'll slice it at an angle. Depending on how you slice it, you end with a conic section. You can end with a circle, you can end with an ellipse, a parabola, or a hyperbola. Now, each of these conic sections have their own features, but what I want you to remember about them is that when you talk about the graph looks like the problem that we have here on the screen, x squared plus y squared minus 4x minus 10y plus 20 equals 0. And most of the time these conic sections are not functions. So for example, a circle or an ellipse or a parabola on its side, these would not be considered functions because for each input you don't have exactly one output. The other thing to consider here is that when you talk about these functions, there was no way to solve for y. And these are great examples of implicit functions. Implicit functions are functions that we cannot solve for y. An explicit function is what we are used to dealing with because we can solve it and we can get an equation that is explicitly spelled out in terms of x. So that's what it means to be explicit or implicit in the math classroom. So let's consider this example. We want to find the slope of the line tangent to the graph at x equals 1. Well, in order to do this for any function, regardless of what it looks like, is you need a point. Okay, well, we can find the point, right? So let's do that. So if this is my equation, I'm going to plug in -1. So I'll have -1 squared plus y squared minus 4 times -1 minus 10 times y plus 20 equals 0. So I have to find the y value, right? So this will be 1 plus y squared plus 4 minus 10y plus 20. Okay, so this ends with y squared minus 10y plus 25 equals 0. And so then I'm going to solve for y. Now this is where it gets a little tricky because I'm going to solve this and I have to factor. And sometimes, here we go, y equals 5. So sometimes what's going to happen is when I find these points, sometimes you're going to have more than one spot, right? So here we only have one answer, y equals 5. So the point of tangency, the point that we're going to use is going to be -1, 5. But let's recall, this is not all we need, and it would be nice if I could write and speak at the same time. -1, 5 is the point where I'm tangent. But we also need a slope. And the slope is going to always be the derivative at x equals -1. So let's take a look at the graph of what we have going on so far. And I can graph this conic section in Desmos. And when we graph it, we actually see that, yes, in fact, we have a circle. And there is a method to get this into our standard form. This is called general form, the way that we have it right now. Standard form takes it and completes the square to get it into a format where we actually can identify the center. And if you look at the green and the blue circle on the screen, it's changing colors as I turn this equation on and off, and sure enough, what this means is that this equation matches the green one. And we see that it is a circle, and let's see, I think we would have to kind of scroll a little bit over. I don't have my keyboard here, but if we scrolled over, we would see that this is in fact a circle, and I'm not sure what the radius is just looking at the graph. But in any case, it's a circle centered at 2, 5 with whatever the radius is. Anyway, when I highlight the point x equals -1, this is where it falls on the circle. And sure enough, -1, 5 is our point of tangency. And if I were to guess based on what I see here, so if I zoom in a little bit, if I were to guess based on this graph, what kind of a line would be tangent at this black dot, you might be thinking to yourself, well, gee, kind of looks like it might be a vertical line. So let's see what happens when I put a vertical line in there. And sure enough, this red vertical line sure does appear to be tangent to the circle at x equals -1. So let's make a prediction. What kind of a slope would we expect to get if we try to find the derivative of this function? Well, if you remember, a vertical line has an undefined slope. So we would expect to get a value where when we plug -1 in, we should get an undefined slope. So let's walk through this process called implicit differentiation, and we're just going to see if we meet our expectation, if we are able to get to an undefined slope. So what is this process of implicit differentiation? Well, when we understand that y equals g of x, then we can think of our multivariable equation with x and y as not just a function of x, but a function of x and this other function, g of x. And this kind of reminds me of the chain rule. And really, the way we state this, we've got some different ways to talk about functions. Instead of using f of x when we have an implicitly defined function, we can think of it as a function of x and y. Well, then we would write it as a function of x and g of x, which means when we're differentiating with respect to x, we need to consider that g of x as an inside function. So our chain rule says we have to do the outside-inside rule. Well, as we do the derivative term by term, when we get to something with a y in it, we're going to have to take the derivative of that separately because it's its own little mini function, and the chain rule says not only do the derivative of the outer function, but then tack on a derivative of that inner function. So for example, if I have if I have it written out using g of x, which this may be kind of confusing, but for some of you it may actually clear things up and be easier to understand. So just wait and I'll explain it in another way also. But the idea here is that when we do this derivative, we do 2x for the x's, we do -4 for 4x, because when we differentiate with respect to x, we just do the derivative. But then when we get to g of x, the outside-inside rule says do the derivative of the outside, but then multiply it by the derivative of the inside, so that g prime of x. And we'll have to do the same thing here with this -10, so we do -10, but then we need to do the derivative of g prime of x. So we do the outside derivative, well, 10 times g of x, the derivative would just be 10, but then because it's g of x, g prime of x. And then 20 would be 0, and then 0 would stay 0. Well, this is great and all, but it's pretty confusing when you have all these g primes floating around. So let me show you the more conventional way of what we do, and we'll compare them back to this original, kind of g prime outside-inside rule explanation. So here's what it's actually going to look like. We don't use g of x, we use y. We don't use y prime, we use dy dx. So let's kind of draw some comparisons here. So let's see, make it a little bit on the larger scale so we can see everything. So here we go, the derivative of x squared is just 2x, so that doesn't change. But then, oh, this is out of order a little bit. So the derivative of y squared, that was that g of x squared. Well, the outside-inside rule says do the derivative like normal, so the derivative of y squared is just 2y. But then here's where it's different. That g prime, we're going to write it in there as a dy dx. Really, it's the same thing. So times dy dx. -4, because it's just x, so we just treat it normally. Derivative is just going to be -4. -10y, so -10, but because it's a y, we're going to multiply it by that derivative. It's that outside-inside rule. dy dx. 20, the derivative is 0. So now we have this situation. So instead of using g prime, we were just using dy dx. Now, if none of that with the chain rule makes sense to you and you're just kind of like, whoa, 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 here's the easy thing you need to remember. When we do implicit differentiation, you do the derivative of everything normally. So x squared is 2x, y squared is 2y. Just do the derivatives like normal. But when you come across anything other than an x, you have to throw a dy dx in there. And as a matter of fact, the rule isn't just x, it's whatever's in the denominator. So if you're trying to find dy dx or dv dt, and there's any other letter except for whatever's in the bottom of the derivative you're trying to find, that value in the bottom, that variable, is the one you're differentiating with respect to. So suppose you have a volume problem and you have an r and an h and you want to find dv dr. Anything that wasn't r, you would have to throw a dv d, or a dh dr, or whatever it is. So we'll try to come up with some different letters and see if we can, make that a little bit more clear for you. But the idea is this bottom value in your Leibniz notation for the derivative tells you what you're differentiating with respect to. Any letter other than that is going to require some sort of dy dx equivalent. So let's keep going. So step 1, differentiate with respect to x. Done. Step 2 is to gather any like terms. So what we want to do is we want to gather all the dy dx's together and put everything else on the other side of the equal sign. And we do that using addition and subtraction. So I'm going to keep the 2y dy dx minus 10 dy dx. And then what I'm going to do is I'm going to subtract the 2x and I'm going to add 4. So minus 2x plus 4 to both sides. So that gives me this equation. Then what I'm going to do is I'm going to factor out dy dx. And when I do that, what's left is 2y minus 10. And then all I have to do is a little bit of algebra here, and I'm going to divide out that 2y minus 10. And so this is the derivative, dy dx. But this is not all we're after. Remember, our goal is to write the equation of the line that's tangent to this circle. We want a point of tangency at -1, 5. So that was the original point that we found up above. So this is our point of tangency. So this is x and this is y. So here's what we're going to do. When we have an implicitly defined function, then usually our derivative is also an implicit derivative. Notice we have an x in the numerator and a y in the denominator. So what I'm going to do is I'm going to evaluate this derivative at the point -1, 5. And the way that I would write that looks like this. Here's my notation. I'm going to say dy dx, and then I'm going to draw this line. This line means evaluated at, and then -1, 5 equals. So anytime, if I'm using my AP exam, if I'm using my calculator or anything like that, and I go to plug a number in, using this notation is a way of expressing that you are finding the derivative at a spot. Here we're using -1, 5. You could also write it as x equals -1. That would be another acceptable way to say I'm evaluating the derivative at -1. So lots of different ways, but dy dx, line, x equals -1, or the point if it's implicit. And then if you can do it in your calculator, you just do it in your calculator. Here I'm going to write it all out. So I'm going to have -2 times -1 plus 4, and then the denominator 2 times 5 minus 10. Well, you guys, we knew it was coming. We get 7 in the numerator, we get 0 in the denominator, which is an undefined slope. So we have a vertical line. And the equation of a vertical line is x equals the x-coordinate. So the line that's tangent, sure enough, is x equals -1. Now this is what we predicted based on the visual. On your test and on your AP exam, you're not always going to have that visual to rely on. When you do, you should use it to confirm your results. That's called confirming your results graphically. So this met our expectation. It was a vertical line, undefined slope, x equals -1. So now what we're going to do is we're going to try a couple more problems, and we may change up the letters here, but whoops, we just did that point. But now we're going to start out simple, and if you want to pause the video and kind of work them out on your own, I would highly encourage you to do that and then check your work with the results here in just a moment. I'm going to keep going for anybody who wants me to work this out. So remember, here are our steps, and let me just kind of review them on the screen if you want to pause and write them down. Here we go. Step 1, take the derivative of each term with respect to x. When you take the derivative of anything other than the x or whatever variable's in the bottom, throw a dy dx in there. So just throw a dy dx in there. 9 out of 10 times it's x and y. But I'll show you one that's not x and y here too. So those are our steps. Now let's take a look at what it is when we apply them. So here, as we start, we're going to do each derivative with respect to x. So here's y, so I'm going to throw a dy dx in there. And then the derivative of x is just 1. So now I don't need to gather anything on either side. This one's nice and easy. I'm going to go ahead and divide out that 2y. Whoops, 2y, 2y. So here dy dx is simply 1 over 2y. That's what I have. That's how I do it. So hopefully that's what you got if you were working on your own. So this one says find the slope of the circle, x squared plus y squared equals 25 when x is 3. So let's do it. First things first, take each derivative with respect to x. So we have 2x plus 2y, but since it's a y, I'm going to put dy dx in there. Now, don't forget that the derivative of a constant is always 0. That's something people tend to forget, and they get it wrong because they keep the 25 in there. If you find that you're having a hard time solving for the dy dx, just go back and double check that your constants all got zeroed out. So now I'm going to gather my terms. 2y dy dx equals negative 2x, because remember I am subtracting 2x minus 2x. So now I'm going to go ahead and divide by 2y, and dy dx is, the 2's cancel, negative x over y. Now we want to know the slope when x is 3. Well, my derivative has an x and a y in it, so I actually need to back up and find the y value. So x is 3, so I'm going to plug 3 in. 3 squared plus y squared equals 25. 9 plus y squared equals 25. Y squared equals 16. So what is y? Oh my goodness. Well, when I square root this, I'm going to remember that when I square root y squared, I actually get the absolute value of y. That's technically what's happening, which means when I remove that absolute value, the absolute value could be positive, or the value that's inside the absolute value bars could be positive or negative. So what does y equal? Y equals 4 or negative 4. So actually I'm going to have two spots, and we'll see this graphically here in just a moment. But there are going to be two slopes to this circle where when x is 3, there's going to be two different options. So let's find out what the two slopes are real quick. So dy dx, so we're going to evaluate one at the point 3, 4, and then we're going to have to find it again at 3, negative 4. So we're evaluating two different slopes. So here we go. It would be negative x over y, so negative 3/4, or negative 3 over negative 4, or just positive 3/4. So we have negative 3/4 and positive 3/4 are the two slopes of the lines. Let's take a look at what the graph looks like, because you know it's always good to see a picture and confirm what's going on. So here we are at the graph of this circle, and you can see that, oh, when x is 3, yep, here are the 2 points on the circle. And then when I take a look at the two lines, so one has a slope of negative 3/4 and passes through 3, 4. So here's a picture of that one. Hey, it's a point of tangency, and this line has a slope of negative 3/4. The other one has a positive slope of 3/4, and there it is. And it passes through a slightly different point, so you can see the y value is y plus 4. But in any case, this is a great example of the fact that when we have implicitly defined functions, it's not always the case that, you know, there we go, that's a little bit better. It's not always the case that you're only going to have one possible answer. Sometimes you're going to have more than one, because these implicit functions are things like circles and ellipses, and they're technically not functions, so there's more than one output for every input. So let's try another example. Here we go. We've got the derivative of 2y equals x squared plus sine y. So I'm going to do each derivative separately. So the derivative of 2y is just 2, but because it's y, I'm going to put a dy dx in, because differentiating with respect to x. So then I'm going to have 2x. I don't have to do anything, right? But then sine of y. Ooh, this is a great chain rule example. So I'm going to have to take the derivative of sine of y, which is cosine. But because there's a y in the angle, I'm going to then multiply by dy dx. So now I have to gather all the dy dx's over. It'll look something like this. 2 dy dx minus, I'm going to put the dy dx in the front so I don't get confused, cosine y, there we go, equals 2x. Factor out the dy dx, 2 minus cosine y. So then dy dx is just 2x over 2 minus cosine of y. So there's my equation. I just needed to find the derivative. I don't need to plug anything in right now. But that's a great example of, having a trig function in there. Now, let's talk a little bit about what happens when we need to find the second derivative of a implicitly defined function. So before we can find a second derivative, we have to find the first derivative. So here's our example. We want the second derivative for 2x cubed minus 3y squared equals 8. So I'm going to go and I'm going to find the derivative normally. So 6x squared minus 6y dy dx equals 0. Don't forget to zero out those constants. So now here we go. 6x squared. I'm going to add 6y over. And then I'm going to divide by 6y. So x squared over y equals dy dx. So now there's my first derivative. Now I'm ready to find my second derivative. And as you can see by my lovely little graphic here, we're going to be having to do some back substitution. So let's see what Mr. Surprised and Excited is so surprised and excited about. Here we go. So if dy dx is x squared over y, then the second derivative, pay attention to what's being squared here, the d on the top and the x on the bottom. I'm going to have to use the quotient rule. Dun dun dun. Quotient rule. So by now, hopefully we have this memorized, or we're getting close. So the quotient rule is this. High d low always comes last. So that means we start with low d high, derivative of the top, minus, we have to move Mr. Surprised here, give ourselves a little bit of room, minus high d low. Now the derivative of y is just 1, but because of that we have a dy dx because it's y, all over low squared. Now, we're looking at this, and I'm going to clean it up a little bit, and I need to get rid of that dy dx. That's not okay. So as I clean this up, 2xy minus x squared, this is bothering me right there, that dy dx. But wait a second, Mr. Surprised here is telling us we need to use back substitution. Well, didn't we just find dy dx? So couldn't we just replace dy dx with x squared over y? The answer is yes, and that's what we're going to do. Now, I'm going to show you a little bit more algebra here, because on your AP exam, even on a free response, there are a couple of simplification expectations. One of them is you're not allowed to leave trig functions involving unit circle values. So if you came across a tangent of pi over 4, you'd be expected to replace that with its value from the unit circle, which is 1. Here is a great example of another type of simplification that's expected, and that's when you have complex fractions or fractions within another fraction. You have to do something about that. So let's see what we're going to do. 2xy minus x to the 4th over y, all over y squared. To deal with this, I'm simply going to take this y squared in the denominator, I'm going to put it over 1. Then what I'm going to do is I'm going to flip and multiply everything in the numerator by the reciprocal. Now, I could actually just stop here and write it as 2 factors being multiplied. But for the sake of being, complete and thorough, I'm going to go ahead and distribute that to everything. And when I distribute it to everything, each item in the numerator turns into its own little fraction. So 2xy over y squared minus x to the 4th over y cubed. And I could leave it like that, or I could recognize that I have one more way to simplify, and that is just to go 2x over y minus x to the 4th over y cubed. I could also work it through and try to get a common denominator. That might be something that you would be expected to do to match it up with a multiple choice option, but I'm going to stop right there just because I want to make sure you understand how far you need to go in a free response. So let's keep going. Let's see what other examples we can do to practice here so we can become really good at this. Now I promised one more example where we don't use x and y, just so we can really understand this whole idea of differentiating with respect to something. So if I wanted to find dA dB for this function, it might look something like this. I do 2a, and since a is not that bottom value, I'd have to multiply by a dA dB. But then I'd have 2b equals 0. Now when I solve for dA dB, I would follow the same steps. I'd gather the terms on each side and then divide to get rid of anything that is in my way, negative b over a. Now likewise, suppose I wanted to find dB dA. Well, that might look a little different. This time I'm differentiating with respect to a. So I'd go 2a plus 2b, but then I'd multiply by the dB dA over here next to the b. And so my final result, dB dA, when I do my magical algebra subtracting things like that, would be negative a over b. So you can see there's a little relationship there with the dB dA versus the dA dB, and that's not coincidental. But this is just something to kind of like drive home that idea of differentiating with respect to that bottom variable. That's a really important thing to understand. Hopefully this has been a good explanation for you. Remember, you're only going to reach mastery by first becoming proficient through practice. So keep at it, and I know you guys can do this. I know you can be successful, so you've got this.